So this is the classic Atwood machine kind of problem. You have a pulley with two masses on a string. In this case, they're uneven weights, so that we should be able to determine that it should go in one direction. If this started at rest, which it does right here, since this has a greater f of g, it says 36, then it is should pull more than this f of g, which is only 16. So I kind of did things a little bit differently here. Normally you'll get masses, but this time I gave you the weight instead. So you just have to be careful when you do see this. Remember, this is newtons is weight, but if we want it in kilograms, we could just divide it by 10. So normally when I start going into forces, instead of using g as 9.8 meters per second, I start rounding it off to 10 meters per second. And the reason is because it's just much easier to do in your head. And a lot of standardized tests actually go with 10 just because if you don't have a calculator, or even if you do, it's just much faster and much easier to solve in your head. So for force problems, I will most likely use 10. So here, remember Fg is equal to m times g. So in this case, we're looking for m, which is the mass. The force is 36, gravity is 10. So if you divide it, 3.6 kilograms equals the mass. So we could just divide it by your head mentally, or you could just do it out. So 3.6 kilograms is the mass. This one will be 1.6 kilograms. All right. So in an Atwood machine, the first thing I usually like to do is to draw all the forces. Gravity is something that's always present. So we have force of gravity here, 36. Force of gravity here, 16. Let me just label this one as B and this one as A. And then there is things holding it up. So in this case, it's going to be tension. So tension will be, let's see if yellow shows up. No, kind of. Let me choose it. Choose a different color. Let me just do green. So let's say tension is green. And it's going to pull up on the both of them, and it's going to pull up actually the same amount because it is the same string. So tension is going to be the same on both of them. What we don't know is what's actually going on. So the first question is, what's the acceleration of the system? And when you're doing acceleration, you always want to use the system, meaning by the whole thing. If you just focus on just one of the blocks or one of the items, what's going to happen is you're going to have multiple unknowns. So I can put it down here. So if we wanted to find the tension of the string, you do want to only focus on one box. So if we do, let's say we focus on box A. Here we have two forces, force of gravity of A, which is 36. And then you have tension. Now, if you're looking for acceleration and you did the sum of all forces is equal to, in this case, there's two of them, FGA plus T. And then if you kind of make sum of all forces equal to MA, so you have MA equals 36, and I'm not going to worry about signs right now, plus T. You'll notice that we do have mass, but we don't have A and we don't have T. So you have two unknowns. So that's why when you're solving for acceleration, you can't just focus on one box. You need to look at the whole system itself. So we're going to do that. So we're going to look at sum of all forces of the whole system. Now, when we're doing this, we want to make sure our signs are correct. Because the pulley actually changes direction of force, we have to be careful here. This gravity is pointing down. This gravity is pointing down. But they're not working with each other. They're actually working against each other. Because if this one pulls down, it's actually pulling up on the string. So we have to do something called direction of motion. It doesn't really matter which way you go. It usually makes sense to go the way that you think it's going to go. But even if you get it guessed wrong, the only difference will be sign. So really, direction of motion is there to help you determine the sign. So let's say, since this is a bigger number, I'm going to say it's going to go up on this side, over on this side, and then back down. That's going to be my direction of motion. Or DOM. And what that means, like I said, the main thing I care about is sign. I want to determine my sign based on this. So let's see. If it's in the same direction as the direction of motion, it's going to be positive. If it's in the opposite direction, it's going to be negative. So these two are opposite direction, negative. These two are same direction, positive. Opposite direction, negative. Same direction, positive. So even though it doesn't make sense that positive is down, we know that at least here, this force of gravity is working against this force of gravity, which I like. This tension is the opposite of this tension. Remember, strings always pull towards one another. So overall, I'm happy with the signs. Even if you do direction of motion the other way, it's still going to correspond the same. F and G's are going to be opposite, T's are going to be opposite. So either way, it's okay. So I'm going to put all my forces in. I have force of gravity of box A, tension, tension, force of gravity, oh, I forgot to put a B there, force of gravity, box B. Then I'm going to write down my units, or not my units, my signs. So this one's a plus, minus, plus, minus. And remember, our goal is acceleration. So it's okay that my tensions cancel out. We want them to cancel out because it's one of our unknowns. So now we're left with sum of all forces, which is also equal to ma, force of gravity of box A minus force of gravity of box B. Okay. Then what we're going to do is just plug in our values. 36 newtons minus 16 newtons is equal to mass times acceleration. Now the tricky part is figuring out what this mass is. Since it's of the whole system, we're going to add all the masses in the system that we included. So that's going to be 16 plus, oh, I messed up, 1.6 plus 3.6. I almost messed up on my own trick there. So remember, newtons is weight, but mass is kilograms. So if I could do this in my head, 5.2 kilograms. So yeah, 5.2 A equals 36. Oh, let me just do the math. Is equal to 20 newtons. So A is equal to 20 divided by 5.2. And get 3.85. And let me make sure all my signs are correct. So it is positive. All right. Let me make sure I did my math correct. 36, 16, 1.6 plus 3.6. Yeah, okay. So I got all my math correct. It's positive 3.85. Remember, this positive is in relationship with what I determine as my sign. So it is acceleration up on the right side, down on the left side. Now, since we have this, now we can work on this one. So now, even though we had two unknowns here, now we have one of the unknowns. A is 3.85 and it's for the whole system. So both box B and box A will have the same one. So now I'm going to have my A, which is 3.85 meters per second squared, equals 36 plus tension. Now, before I move on, there's two things you have to be aware of. First one is this mass. So it is not 5.2 this time, it's actually 3.6 kilograms. And the reason is because we're focusing on this one box, in this case box A, so we're only going to use the mass of box A. So 3.6 kilograms times the acceleration equals this. I want to do one last thing, which is a check on acceleration sign. This is positive, but remember, positive means down. So this positive should match this one because both FGA is down and both acceleration down. So these two should have the same sign. They do in this case, so I'm happy. Let's do the math here. 3.6 times 3.85. And I get 13.86 newtons equals 36 newtons plus T. Move it over to the other side, minus 36. And I get negative 22.14 newtons equals tension. So right here, I said that this should be a negative, and it is. In this case, it is negative 22.14. And at the same time, tension here should be smaller than F of G because it is accelerating downward, and it is. And then you could do another check. If this is 22, this must be 22.14. This tension should be bigger than this force because in this, on the right side, it's accelerating upwards, and it is as well. So this is how you kind of solve it. You kind of break it down. First, find acceleration of the system, then you can find tension within the string, and hopefully that helps. All right. I like this problem because it's simple, but yet it gets kind of complex on the second question that I asked. So it's simple because all it is just thinking a thought process of what's actually happening. And we have multiple strings in this case, and we have two fish. So it says a fisherman pulls up fish. One of them is attached to another. So here's my initial line. I have a fish on the top, and then I have another fish on the bottom. The top fish has a mass of 2.5 kilograms. The bottom fish has a mass of 1.5 kilograms. And then it does say that they're 0.4 meters apart, but that doesn't really matter here. What we know is that we have this. Another thing that I do say is that it's at constant speed. So the first question is kind of redundant, but is there just to make sure that you're keeping up. It says, what was the acceleration of fish? Well, if it's constant speed, then acceleration is equal to 0. So remember, acceleration is equal to change in velocity over time. If it's constant, that means there is no change. So it's 0 over t, or just 0. All right, so here's my thing. There's two ways of doing this. You could do it kind of like a thought process. You could think in your head what's going on. And then I'm going to show kind of the process itself by the summation. And either way is fine, but the other way is always going to work. So I kind of want to share my thought process and then share the math itself and see which one works for you. So let's call this fish A, this fish B, this tension 1, or string 1, tension 2, or string 2. So our goal is to find these tensions. We could do it through a thought process. If A is equal to 0, this is possible. So let me make gravity blue. So let's focus on the bottom one first. I usually like working bottom up. To me, it just makes more sense. This has a mass of 1.5. So gravity's pulling down. Gravity's pulling down with mg. Mass in this case is 1.5 kilograms times 10 meters per second squared, so I get 15 newtons. Now, if acceleration is equal to 0, so that means my forces is going to equal but opposite. So since the fish only feels one force against it, which is the string up, so this is T2, if it's not acceleration, it has to equal this, but the opposite sign. So this one's down, so it's negative. This one has to be positive 15 newtons. Since it's a string and it's taunts, remember, if it's not taunts, if this was snipped, then the fish will just be able to swim free. Since they're connected, it's not snipped. So that means there is a force of tension, also equal and opposite as this one, so it's also 15 newtons. Now the top fish is also feeling gravity on itself. So it has a force of gravity, and that force of gravity is also mg, so 2.5 times 10 will give you 25 newtons. And this is also down. So that's all the forces towards the bottom. At the top, the fish is supported by the string, T1, and it's supporting not only the weight of the top fish, but it's also supporting the weight of the bottom fish, which in this case is represented by T2. So you just add these two up. This one is negative 15.25, so this is 40 newtons positive. So that's kind of the thought way. The formally way is just to do summations. So if we just focus on fish B, the summation is the two forces here, T2 and FG. FG plus T2. MA equals FG, in this case is negative 15 newtons plus T2. What's nice is if A is equal to 0, then you have this. And then all you have to do is move the 15 to the other side. and you get T2 is equal to 15 newtons. So exactly what we did here. The next one, we focus on fish A, and we also have a summation. This one's going to be a little bit more complicated because instead of two forces, this fish is feeling gravity, tension, tension. So T1 plus T2 plus F of G of itself. So we'll call FGA. So again, since A is equal to 0, this is equal to 0. T1 is our unknown here. T2 we do know, which is 15. In this case, the string is pulling down, so it's negative 15 newtons, plus FGA, which is also a negative 25. So when we add these together, you get 40. Move it to the other side, so T1 is equal to positive 40 newtons. So whichever way works for you in my class, I prefer always working out the answers just in case you make a mental mistake, your work is there. Okay, so this is when acceleration is equal to 0. You can do it in your head, but it's usually better to work it out. Now, when acceleration is not 0, in this case, positive 1 meters per second, it really is better to do this. So it's exactly the same problem. Here's fish 1, here's fish 2. This one was 2.5, this one's 1.5. So the gravities don't change. This gravity is still negative 15 newtons. This gravity is still negative 25 newtons. Remember, gravity only works on mass. It doesn't care what you're doing. Gravity always pulls the same amount. You could feel lighter or weighter because of what Fn's doing, in this case, what the string's doing, but gravity always does the same thing. But since it's now accelerating upwards with an A of positive 1 meters per second, the tension technically should be bigger. So let's figure out what that is. So in this case, it is better to do summations. And I shouldn't have done yellow. I apologize. Let me redo it in green. So, whoa, what did I do? Let me redo it in green. Okay, so let's focus on the bottom one. I usually like doing that first. So for the bottom fish, so focus on fish B. So fish B only feels one force, which is, two, force of gravity, force of tension. So sum of all forces is equal to tension plus force of gravity. In this case, this is not equal to 0. It's ma equals t minus 15. This mass right here is 1.5. Since we're only focusing on fish B, we're only going to use fish B's mass times the acceleration, which is 1. T minus 15 newtons. This is 1.5 newtons. So if I move the 15 over to the other side, T1 is equal to 16.5 newtons. Okay, do the same thing, but this time we're going to focus on B. A. Okay, so like I said before, this one has 1, 2, 3 forces. So sum of all forces is equal to T2 plus T1 plus Fg of this fish, which we called A. Once again, this is not equal to 0 now. It's equal to mass, 2.5 kilograms, times acceleration, 1 meter per second squared, equals T2, which we don't know, T1, which we calculated as 16.5. But on the fish up here, it's negative, and gravity is negative 25. So here is my equation. All I have to do is isolate T2. So 2 times 1 is 2.5 newtons equals T2 minus, let's see if I can do this in my head, 41.5. Let me just double check. 16.5 plus 25, 41.5. I'm going to move that to the other side, plus 2.5, right? 41.5 plus 2.5, and I get 44. So that's kind of how you solve it. You'll break it apart into its components if you want to find tension. If you want to find acceleration, you need to usually add them all together, kind of like what we did with the Atwood system. So here's multiple strings, and hopefully that makes sense. If not, let me know, and I'll be happy to explain to you.